गया नहीं कोई नहीं आया आ गया So we are live on the Facebook now, and I'm going to start it formally. Bismillah ar-Rahman ar-Rahim, in the name of Allah, the most gracious and the most merciful. This is technical lecture number 82. Ladies and gentlemen, Assalamu alaikum, good afternoon and good evening. On behalf of Pakistan Society of Civil Engineers, it is our pleasure to welcome all attendees, including those joining us via Facebook. Today we are presenting lecture number 82 in our ongoing monthly series, a tradition we have upheld consistently since 2020. These lectures are part of PSC's commitment to fostering knowledge exchange, offering both emerging and experienced engineers the latest insights across various civil engineering disciplines. We encourage all participants to join us in our mission to strengthen PSCE as a dynamic and influential platform dedicated to the advancement and dissemination of knowledge. Before I proceed with the topic and introduction of the guest speaker, it is my responsibility to read out the rules set out by Pakistan Engineering Council. Participants registered for CPD points are required to appear live on webcam. However, female participants have an option to cover their faces if they wish while appearing live. To ensure a smooth session, the microphones of all participants except that of the speaker will remain in a mute position throughout the lecture. A dedicated 20-minute question and answer session will take place at the end of the lecture. Please note that questions during the lecture should be submitted via chat box only. You can type your questions during the lecture in the chat box. At the end of the lecture, I shall read out the questions which the guest speaker will answer. Now, participants joining us on the Facebook also have the same facility. They can type their questions in the chat box, and we will read out the questions from the chat box for the speaker to answer. Now, today's topic is pile design and construction practices, including aspects of pile integrity and dynamic load testing. And our August speaker today is Dr. Martin D. Larisch. First, an apology to Dr. Martin. We have given him a trouble today at a very odd hour. It's almost 9 p.m. in New Zealand, and we are sorry for that, but the lecture is very important. The speaker is very important. So I hope everybody will take advantage and listen to the lecture carefully, and hopefully it is going to be a very knowledgeable lecture. Dr. Martin Larisch is a fellow with Engineers Australia and Engineering New Zealand. With more than 25 years of international design and construction experience in the piling and ground engineering sector. For almost 2 decades, he has worked in various technical and operational leadership roles for some of the largest specialist piling and ground improvement contractors in Australia, New Zealand, and Germany, and has significant experience in the design, construction, and verification of piles, retaining structures, and ground improvement schemes. For the last 8 years, he worked as principal engineer in the design and design verification of piles in seismic and non-seismic regions. He is also acting as an independent expert for disputes and their resolutions concerning defective piles and retaining walls. Dr. Larisch was affiliated with the University of Queensland in Brisbane as an adjunct associate professor in the Geotechnical Engineering Centre from 2014 to 2021. He published more than 30 technical papers in the fields of piling, retaining structures, ground improvement, working platforms, and tremie concrete, and has been involved in various international committees and working groups to develop best practice industry guidelines for piling and ground engineering works. So this was a very brief introduction of Dr. Martin. And Dr. Martin, the floor is yours. Please go ahead.
Thank you, Mr. Tahir Sultan, for the kind introduction. Thank you in particular to the Pakistan Society of Civil Engineers for the opportunity to provide this guest lecture. It's a great honor for me to do that. And welcome everybody. Just about to share my presentation. If you can let me know if you can see my screen.
Yeah, it's moving. It's okay. You can go ahead.
Perfect. Seen that. And yeah, really thank you for joining. It's a great honor and privilege to be here. This lecture will cover some practical aspects of piling, some fundamentals of axial pile design and lateral pile design. I understand the audience, engineers from different backgrounds, geotechnical, structural, civil, different levels of experience. So we will cover the fundamentals of axial and lateral pile design, and then get into pile construction and pile verifications. So we will have the entire life cycle of a piling project, from the design over construction and verification. I will also highlight a few things. It's not very complex, but really understanding the key parameters in pile design and how we can, or how pile construction can impact the load settlement behavior of piles of different pile types. And then lastly, pile verification, describing what these different methods, how they work, and also what they can and what they can't do. And yeah, it will be a packed session, lots of information. And I want to start with a bit of health and safety from own experience. We're drilling holes in the ground. We have to make sure that we don't hit any assets, any underground structures. And I've worked mainly in my career in Australia, New Zealand, 5 years in Germany. But what we sometimes find is that the services are not located where they're supposed to be. And it's can be very dangerous for the piling crew, for the public, to hit these services if they are undetected, and could be significant damage to health and safety and to assets. So really want to start at the basics. When do we need foundation piles? And usually in piling, we transfer structural loads to transfer into deeper and stiffer soil or rock layers. And we want to achieve an adequate load displacement behavior of the foundation. And we only use piles for foundation of structures if a shallow footing can't provide these load displacement behaviors. Could be under static conditions, could be under seismic conditions. And we will look into basic piling techniques used in Australia, mainly in New Zealand, probably around the world. I really focus on board piles and driven piles, and just explain the main design and construction principles. And based on my own experience, also highlighting what can go wrong, how can we significantly over and underestimate the pile behavior. And also a perspective, I will try to provide a perspective on influence on installation effects and pile verification methods. So actually many years ago, I did my PhD on pile installation effects, because as a young engineer, I was on site and couldn't understand on some projects. We did the thorough design, the thorough investigation, the thorough design, and then we did the testing. And the pile load test results were different than expected, even though the ground conditions were similar. And then we looked at the different, we back analyzed the load testing results. We saw that in certain soil layers, the resistance, the soil resistance, was significantly lower than expected and lower than in textbooks. And then I did a lot of trials and finite element modeling to find out what happens. And so that was part of it, and I will share a few of these findings today. But if we really go back to the basis and say, what is the purpose of deep foundations? So we transfer usually high vertical building or structural loads in the ground, and we bridge any soft or unsuitable ground conditions. And the loads will be transferred into stiffer layers. We can also use that for settlement control and also providing resistance for lateral loading. And usually, if we look at the pile on the right-hand side, if we have an axial load acting at the pile head, usually the pile will transfer the load through shaft friction first. And in order to fully mobilize the shaft friction, the pile needs to move about 1 to 2% of its diameter, usually. So that's the rule of thumb. If we have significantly larger piles or smaller piles, it could be less. But it's always some movement is required. There's never a pile that has zero movement. This is not possible. And once the shaft friction, simplistic speaking, once this is fully mobilized, the pile will act in end bearing. And when it acts in end bearing, and the pile is founded in soil, the pile usually moves up to 10% of its diameter in order to fail. And this is based on load testing over the past few decades. This is also embedded in the Australian piling standard, AS2159. I don't know if this is applicable or if this is an option in Pakistan. I found the AS2159 a very, very practical code that addresses risk in piling very, very well. So there's movement required in order to mobilize the pile resistance, and we will talk about that a lot. We look at load transfer mechanism of different foundation systems. We have on the, well, let's start on the left-hand side, single piles connected to a slab or a beam, and the load will be transferred from the structure into the slab or the beam, and from there into the piles. If the piles are spaced adequately, usually 2.5 to 3 times of their diameter from center to center, they will act as individual piles, and they will transfer the load through shaft friction and end bearing. We can have combined pile groups. It's a little bit more complex, so I won't cover that. So we call them mixed foundation, where the underside of the slab also contributes to the load transfer. However, this requires that the amount of settlement of the piles and the slab is the same. If I would found my piles in rock, the piles have a much stiffer response, and a pile draft foundation wouldn't work. But we won't cover that. And then we have rigid inclusions, ground improvement. I saw that in a previous lecture, Dr. Derek Egan spoke about rigid inclusions. It's a ground improvement method. Even though we will install concrete columns with piling equipment, with these rigid inclusions, we don't connect them to the structure. So the structure is designed with a shallow foundation, shallow footing, and there will be a gravel layer or gravel raft between the underside of the slab and the top of the inclusions. And the rigid inclusions improve the ground. So typically, these elements are not directly connected. We will focus on single piles today. And just to start with, it's very important to differentiate between model and site performance. As designers, we always deal with models, and our models could be simple, could be more advanced, could be a pencil sketch, like on the left-hand side from Broms, with certain relationships about load transfer via shaft, via base, in different ground conditions. And I found that I need to be very careful with these models, particularly if they're taken out of context. And again, this pencil sketch is a model. We try to reflect the reality. And that could be very simplistic, that could be more sophisticated, like the 3D finite element model in the center. And we don't always need finite element models. Probably in my experience, only 1 or 2% of all pile foundations are based on finite elements. Very often, very simple for axial pile design. Almost hand calculations are suitable. And the input parameters always influence the output. Very often we think about the piling methodology and said, which method should I take? And this is important. But in my experience, it's more important to have a real clear focus on the input parameters. And then, of course, if we do testing, we see on the right-hand side a steel pile with some strain gauges and accelerometers. We carried out a dynamic pile load test, and this is the real feedback that I need as a designer. It doesn't happen on all jobs. Probably on the minority of jobs, we get pile load test results. But it's very, very important because that gives us feedback how robust and realistic our design is. And again, this is why in the design stage, I used to provide my settlement ranges of my pile, or the settlement values in ranges, because even if my limit is 25 millimeters, if I probably in my assessment, I get 15, that's probably close enough to 25. If I get 24.9, again, it's an estimate. Until I do a static load test, I don't know, but it's probably close enough, and that would justify a load test. In general, before I start with my design, I would always look at a few generic things. Site visit is always valuable. Understand the settings the piles will be installed. Are there any assets that need to be protected? Is it next to a railway line, next to a road, next to a boundary, next to a highway? Are there some power lines, pipelines? What is the correct piling system? Which is my code and standards? During the design stage, think about temporary works like working platforms. Who is responsible for that? In general, piling is a risky business, and we need to give them the attention. And I'm always getting nervous when I hear people say, "Oh, this is a simple job." There are no simple jobs, and this is the risk I experienced a few times when particular piling jobs are underestimated. We may get into trouble. Another thing, always work within your area of competence. Sometimes structural and geotechnical aspects are equal. They are equally important for piles. And particularly for the colleagues that are early in their career, we can't know everything at first or when we leave university. We have a very basic knowledge, but we learn as we grow. And if your structural competence or geotechnical competence is still fresh, reach out to your colleague, to your boss, and ask questions, and don't overestimate. Be brave, be bold, but also be very careful and use the opportunities to learn. If we look at risk management in general, and again, this is just setting the scene. There are several approaches to manage uncertainty, and I took these three main factors from Australian piling standard AS2159. And we will see that later, that AS2159 will put some risk rating when we have a project and we look at these things. And they said, look, what about your ground conditions? What about your design? And then the installation and construction verification. And if we start with the ground condition, what's the complexity of my site, the geotechnical complexity? If I would say, I don't know, I don't have any boreholes, this is probably a high risk. And I have to rate that, and this affects my geotechnical strength reduction factor or my factor of safety. And the more risk I accumulate in these, what are the 8 different assessment types, the higher my risk, the higher my factor of safety. And it's a really good assessment. The same thing with the extent of ground investigation. One example is sometimes we went out and we say, look, this is a piling job, and we did deep piles with rock sockets. We did a lot of investigation of rock, and then for certain instances the building changed, and we had to use stone columns or ground improvement. And the rock was not of interest because the stone columns would not penetrate into the rock. So we had a lot of boreholes with rock socket samples, but no investigation of meaningful investigation of the soil and above that. So even though the extent of ground investigation was high, the amount and quality of data for my task was low. And really assessing these things. Same with the design. What is the design method in the area of competence? Even if you use simple design methods, they can be well established, for example, like BROMs or other methods. They are very simple, but they've been around for a long time, and there's nothing wrong with it. Again, what is the method of assessment of geotechnical data for the design? So how do I do that? Do I have a laboratory testing? Do I have simple correlations? There's nothing wrong with it, but it's just a different risk level. And then what method of utilizing results from on-site testing and verification? For example, pile load testing. And Australian piling standard AS2159 in particular rewards load testing. So we can increase our geotechnical strength reduction factors from 0.5 to, for example, 0.65 if we do only between 3 and 5% of load testing of our working piles. So for a project with 100 piles, we do 3 to 5 tests. we can increase our strength reduction factor or reduce our factor of safety. And then the last thing is installation and construction verification. What's my level of construction control and performance monitoring? So these are all the things that go through my head at the beginning, but think about it, I can then basically map out my design. And then very briefly, for the design, it's important to differentiate between displacement and non-displacement piles. Again, there's this little table here. Displacement piles are usually driven piles, full scale-driven piles, not open-ended steel liners or steel H-beams, but for example, precast concrete piles. When you drive them, they displace the soil. And when they displace the soils, they may improve the ground conditions. So you may get better, higher friction or end bearing data than in your investigation. Contrary, non-displacement piles like board piles, you drill a hole in the ground, you relieve the stresses, and in these cases you may get lower, you may reduce your initial strength of your ground, and then you have to think about the support, and we'll talk about that later on. Don't want to get too much into ground investigation, but a rule of thumb is it is good practice to go about 3 to 5 pile diameters below your anticipated pile toe level. And you may think, hang on, I don't know how deep my piles are going. I haven't done a design. But even if you start somewhere, do an initial design, if you have your values for a 10-story building and you know from experience, for example, I have 50,000 kilonewton overall load for a building like that. You have about 100 piles, you divide 50,000 by 100, so 500 kilonewton per pile. If you know your ground condition, you can say, yeah, about 10 meters, 12 meters deep. And if you then say, look, your boreholes, probably assuming piles 600 millimeter diameter, if you go 3 meters deeper, you go to maybe 18 or 20 meters. Or a little bit deeper depending on your ground conditions. And maybe stagger your investigation. Tell your client, look, I use 60% of the budget for an initial investigation. And then when we find areas and pockets where we say, oh, we have to go back, we take the rest then. So this is very important. We can use boreholes, we can use cone penetrometer testing or other methods. Usually, if we get boreholes, they're deep enough, we get information about soil types, soil layers, groundwater, any areas where we have core losses, where we don't retrieve any soil samples. Could be a layer of cobbles or very soft soil. That's very important for the designer. Then we get an indication of soil strength with SPT levels, standard penetrometer tests. We can do them every 1.5 meters. Where we basically measure the resistance of the cone over 300 millimeters depth. If we use a 63.5 kilogram hammer over 760 millimeters drop height, and then with these SPTN values, we can get into our design tables and make an assessment of the soil strength, depending if the soil is cohesive or granular. Then we can use cone penetrometer testing or DMT. It's a lateral assessment, dilatometer testing, or geophysical methods, but always in combination with boreholes because we have to correlate our shear wave velocity. The key parameters for my axial and lateral pile design is really I need to understand my soil type. Is it granular or cohesive? How many layers do I have? What's my soil behavior? Is it drained or undrained? Usually for long term, I would always recommend to use drained behavior. Liquefaction risk if we're in seismic areas, if applicable. And I just noticed that there was a 5.0, 5.6 earthquake in Brisbane earlier today, and I worked in Brisbane for 12 years, and there was always saying, no, there are no earthquakes in Australia. And I went to New Zealand, everything is designed for earthquakes with big seismic hazards here, but Australia is not prepared for that, so they suddenly probably have to start rethinking and say, look, what is it? What does it mean? A 5.0 earthquake will trigger some liquefaction. But again, that's a different story. Soil cohesion, I would usually assess cohesion with great care. because it can be variable. It dominates strength at low depth, close to the surface. If your cohesion values are too high and you get a rain event or your soil due to movement, the stiffness weakens, then we may get lower values, and that could be less beneficial for your pile design. Sometimes we need soil permeability, mainly for durability assessment. If you have contaminated water or salt water that may attack the pile. Material, the steel or the concrete, Poisson ratio in some instances, on the soil model if we're getting more sophisticated. We should use saturated drain strength, and we need quality effective strength testing, ideally triaxial testing, and we can't obtain it from a quick triaxial test. If we do triaxial testing, the quick tests are much cheaper, but they only provide you with undrained shear strength. So keep that in mind. Quality data are the key. And personally, I wouldn't mind simpler tests, but having more reliable data. And if we then get into different loading conditions, we look at stability assessments. If we go into limit state design, so that's when we say, look, what is the when does failure occurs, or when we have excessive deformation of the structure or foundation? When do we lose loss of equilibrium of the structure and the ground? And this occurs usually if pile head movements are about 10% of the diameter. And we've seen that in static load test, if the displacement is more than 10% of the diameter, the pile will just keep moving. Then the other thing is serviceability design. So this is deformations of the structure due to ground movements. And again, it's not, it doesn't jeopardize the stability of the pile or the structure, but there are probably non-structure elements affected. And the structure won't fail, but the formations may not be acceptable. We may see cracks in the building. And usually we cover serviceability with pile shaft resistance, and that usually requires 1 to 2% of the pile diameter. And for the structural pile design, we normally use ULS loads. I see there's a question in the chat. I hope it's okay if I directly respond to that from Soraya Kibria. Dr. Martin, our piles are often in groups.
Dr. Martin, go ahead. Go ahead. You can directly respond.
Okay, perfect. Thank you. Piles are often in groups. Does not the serviceability limit state controls their load carrying often than the ultimate, often requiring 10% movement of pile diameter? This is absolutely right. In pile groups, usually serviceability is governing. For single parts, usually both is governing, but you're right, in pile groups, serviceability controls that, because if we assess the pile group of, let's say, 9 piles, we have this block of soil and piles combined. And as a rule of thumb, the settlement of a pile group compared to a single pile is usually twice as high as for the single pile. It could be higher. But yeah, thank you for this comment. This is absolutely correct. For pile groups, very often the 10% doesn't apply. The same applies for rock. We will talk about rock socket design later on, but in rock you will not be able to move the pile 10% of its diameter. This is not possible, and then the concrete strength becomes the limiting factor. So in my experience, if your rock strength is more than 10 to probably 15 MPa, it will be very difficult to fail the rock axially. Again, depending where it is, if it's close to an edge or something like that, different. Now the question, what could be done to consider the effect of over-consolidation induced by basement excavation? Oh, that's a very specific questions. Basically, monitoring is the key. First of all, understanding that there may be effects of over-consolidation with ground investigation, with lab testing. If we know that over-consolidation occurred, and basement excavation is always critical, because it may cause movements of the basement walls, and whatever the basement wall moves outwards at the top, for example, 25 millimeters, there will be settlement of the soil behind the wall. And that will cause settlement of the adjacent structures over a period that varies. But it's usually a differential settlement problem. That could happen at the surface, that could happen to surfaces next to the excavation. But it could also cause a basal heave and a lot of other things. So again, it depends on your material. Yeah, it's a more complex question. But my first consideration would be having a good, or consider that in your site investigation, and then basically design your basement accordingly. All right, I hope that's helpful. If we look at the fundamentals of axial pile design, again, that was the foundation for a high-rise building, 2.4 meter diameter piles.
Dr. Martin, can I interrupt? Just to remind you that I think the continuity of the lecture is very important also. Questions are also important. So
Yes.
wherever you feel the question is to be answered, you are free to answer. And wherever you think the question can be answered at the later stage during the Q&A session, I will read out those questions. So it is up to you. Whichever question you feel is to be answered, you can answer it. Okay, thank you.
Perfect, thank you. Just going on this question, based on numerous pile load tests, I've observed that board piles and so will fail in friction rather than only after about 50 mil settled. The 10 diameter does not work in single as well as group action. No, I can't. It depends on the project, depends on the ground condition, depends on the pile diameter, depends on the pile length, depends on soil, on the installation effects. 10% criteria has worked very well. Done numerous. I probably have done more than 200 static load tests. And again, it's very hard to say that as a general rule. But again, it depends. It's just a rule of thumb initially. But there may be cases where it may not work. All right. If we then look at basics of effective stress design of axial pile capacity. So my total geotechnical resistance is my shaft capacity resulting from surrounding soil and shear, and my ultimate tip load or base load. I have to deduct the weight of the pile, but very often that's neglected in my experience. And then if we look at limit state design, my RG, which is my structure design action effects, which are basically my geotechnical resistance of the pile, similar to my structure design action effects. And this should be the product of my geotechnical strength reduction factor, which is very often we start with 0.5 and then multiply that with my ultimate geotechnical pile resistance. So that means, for example, this is the importance of the geotech strength reduction factor. If my structure load is 1,000 kilonewton, if my strength reduction factor is 0.5, my pile needs to be designed for 2,000 kilonewton. Geotechnical resistance, ultimate resistance for ULS. If I would do some load testing and I could basically increase my strength reduction factor from 0.5 to 0.65, I only have to use 1,540 kilonewton resistance. Depending on my soil condition, I basically cut out about 25% of my resistance. So in some ground conditions, that could mean I can shorten the pile by 25%. So instead of a 20-meter long pile, I may only have a 15 or 60-meter long pile. So that may provide significant savings for the project. Again, it's it needs to be assessed on a site-specific basis. And again, this is how we assess the strength reduction factors in accordance with AS 2159. I mentioned earlier with the ground conditions, geotechnical complexity as a weighting factor of 2. So whenever I rated 5 is very high risk, 1 is very low risk. For example, if it's 5 times 2 would be 10. I put that in my chart as a 10. Same with extent of ground conditions. When I think it's probably a 4, 4 times 2 is 8. So that would be 10 plus 8. And I would go down the list and then I would get my entire sum divided by the number, or divided by 9, and I get my average risk rating. And depending on this average risk rating, I can then assess my overall risk category. And then dependent on my redundancy system, I can assess a strength reduction factor. So the redundancy system means that when I have more than 3 piles, I usually have a high redundancy system. So that means when one pile doesn't work, or if there are any changes in ground conditions, or the load displacement behavior is a bit softer, that means there are other piles that can basically provide or help with the performance. And we see that the strength reduction factors for high redundancy are much higher. For low redundancy, the worst example is always a bridge pile. For a pier, you have a single monopile. And if this pile doesn't perform, there's a big problem for the project. And therefore, we just say this is higher risk, hence we take slightly lower strength reduction factors. And I don't know in Pakistan if you sometimes use AS2159. One more question, your comments on the AEC PILO test interpretation criteria. Or again, this is a very complex question. Maybe we can, if we have time at the end, happy to respond to that. But that probably, I would rather go along first if that's all right. If we look at shaft resistance for axially loaded piles, we mentioned that this is usually the first component of resistance to be developed. Initially, the shaft resistance elastic, fully recoverable, and normally if we in soil, if we get 1 to 2% the diameter of the pile diameter in downwards movement, we fully mobilize it. Again, it's a rule, it's not a fast rule, it's just an estimate, needs to be confirmed by load testing, but it can vary in different ground conditions. If we then look ahead and say, if I make an allowance for certain shaft resistance, how do I verify that, particularly in rock and soil for board piles? And this very often happens through a verification and rock socket cleaning. And that can make a very, very big difference. And for continuous flight auger or CFA piles, it can be the penetration rate. But as a designer, I always start thinking, particularly if my pile design is a bit more aggressive, how do I verify that on site? And again, it's a risk. If I use more aggressive parameters, I need to make sure I can verify that on site. Just making the assumption I use aggressive parameters, but I can't verify that is a risky game. And again, probably remember that from university day, shaft resistance and cohesive soil is your alpha CU method, total stress method. So you use your average undisturbed unranged shear strength of the soil surrounding the pile shaft at the midpoint, and then the surface area of the pile shaft contributing to the support, and you have your adhesion factor. The key risk here is depending which method you use, and I just plotted it. I used the API, American Petroleum Institute method, the ICE method. They have different alpha factors, and the black one on this little chart is our very own New Zealand building code. And you see that the values for board piles and driven piles, usually the rule of thumb is for board piles, you only have 70% of that because you disturb your soil and you relieve some stresses. But depending on your method, you see that alpha values can change. If you use an undrained shear strength of 50 kPa for a driven pile in accordance with the blue line, the API method, I would get about 0.55. According to our New Zealand building code, we'd get 0.8. So that's a huge difference. And we don't change anything. We have the same soil parameters, the same pile diameter, everything is the same. All we're doing is we're using a different method of assessment. This is very important to consider in pile design. The methodology and the standard and the safety concept you use can have a significant impact on your pile design, even if the formulas are so simple like the alpha CU method. If we go into the in granular soil conditions, we have the beta method. It's basically effective stress method. So we have effective pressure at shaft midpoint. And then we have the average value of pile soil friction angle and the coefficient of horizontal stress. So there are some values from, for example, US Army guidelines or other codes and standards. And we can lump this Ks multiplied with tangents delta to a beta value. The key thing here is, which is very often forgotten, this is effective stress, and it needs to be equivalent or smaller than your limiting value of shaft resistance. And there's a little table on the right-hand side. Usually for board piles, in coarse grain soil, it's 100 kPa, fine grain 60, and for driven 150 and 100. So there's a paper from Professor Harry Poulos from 2022 in the Australian Geomechanics Society that shows these limiting values. The reason for that is that effective stress theoretically increases with depth. We see that on the right-hand side with a dotted line. But in reality, we found that at a certain point, your resistance parameters, they don't increase indefinitely. At a certain point, between 10 and 20 times the pile diameter, roughly, they basically keep constant. And this is why it's so important to keep that, to consider the limiting value. There's other research, the brown line that shows basically the resistance at the toe is almost like the effective stress over a short period of the depth. But if you would consider the area beneath the curves of the black one and the brown line, it would be approximately the same. So again, it's really important to consider these limiting values for effective stress design. And we will come to the selection of NQ parameters in various ground conditions for drill shafts in a minute. We then look at end bearing for axially loaded piles. So that's usually the second component of resistance. Its nonlinear behavior can be more tricky to model by linear elastic soil models. Usually it generates bearing failure, and we say it's about 5 to 10% for driven and could be up to 24 for board piles. The reason of this variability is that with driven piles, we can improve the ground conditions beneath the base by installation effects. It's not always possible unless we can prove it. I would not allow for it in the design. And the key things for me as a pile designer are really, how do I verify particularly the cleanliness of the pile base? If I have 200 mil or foot of base debris sitting on my pile, and then I pour concrete, I have a sandwich, and when the pile gets loaded, or the shaft friction is mobilized, and I'm waiting for the end bearing to mobilize, and the pile has to squash through a foot of debris, it will move. And this is really, really critical. Or verification of set and temporary compression for driven piles. Just if we look at bearing capacity in cohesive soils, we have our bearing capacity factor. If we have a 5D embedment into the clay, usually we should have that for piles. And then the question is, how do we assess the undrained shear strength at the pile toe? So this is again quite straightforward. We look at end bearing in granular soils, and we look at the NQ values, the bearing capacity factor, empirical. So it's a function of the bearing capacity factor and the vertical effective overburden pressure. And if we look at different authors, different publications, these NQ values can vary significantly. And again, this is the estimated resistance based on the bearing capacity factor. My vertical effective overburden pressure on the area of my pile base needs to be smaller than this limiting value. And on the right-hand side, in these two tables, on the top, the displacement piles, the bottom, non-displacement piles. So shafts and board piles are basically covered at the bottom. And depending on your soil conditions, from loose to very dense, they go from 1 to 7 MPa. And again, keep in mind that using these values, for example, if I'm in the dense sand, my board pile is 1 meter in diameter, then I take the area of my board pile multiplied with 5. But that means that my pile needs to move about 100 millimeters when it's founded in soil in order to activate that. If can only move 50 mil, for example, because otherwise the building would be damaged structurally if the movement would be too high. This needs to be reduced. And we see that a lot in earthquake engineering when due to soil liquefaction or the shaft resistance basically disappears when the soil liquefies and all the load will be transferred to the base, that we may get bigger settlements, and the structure needs to accommodate that. So this is one of the key things. And again, for example, in some codes and standards, these limiting values are not considered. If you just look at your bearing capacity factor, depending on this factor, you can get very, very unconservative end bearing values. So your pile design may be very unconservative. So why does it matter? If we look at my SLS settlement limit, for example, and let's pick it, it's 25 millimeters. So the red line on the horizontal line is 25 millimeters. If I have a pile which mainly relies on shaft resistance, so basically shaft resistance goes up to a certain point, 1 to 2% of the diameter, and then it flats out. So my base kicks in a little bit. I'll see that on the left-hand side. If I have a pile with less shaft resistance and higher reliance on base, we see that my design load for the same settlement is definitely smaller. Or if I would apply the same load, like on the left-hand side, my settlements would be significantly higher. So this is really a key thing to understand the difference between load transfer through shaft or load transfer through end bearing. And how much that is, it depends. And I saw a question about bentonite slurry reduction of shaft friction, and I will talk about that in probably half an hour, but that can have a significant impact on your load settlement behavior of the pile. So whenever you think your pile will transfer loads, will transfer loading in shaft resistance with lower settlement, if your shaft resistance is only 50% from your assumption, the pile will just carry only half of that and then relies on end bearing. It may not be a stability problem, but for your SLS case, it may become a settlement problem. And this is why sensitivity checks are so important. I do my pile design with my best estimate parameters, and then I say, what happens if my parameters are 20% worse or 20% better? And that gives me a range of pile behavior, and then I can see the robustness of my pile design. If my ground conditions will change, they are not man-made material, but it gives me a bit of a feeling and said, maybe I should use shorter piles with larger diameter, or I should use a larger number of piles with a smaller diameter, and they're probably slightly longer, but I can play around with that. And again, depending on my structure, depending on my loading, depending on my ground conditions. But again, this is the thing, the formulas themselves, they don't have to be complex. It's probably thinking around it, how do I accommodate that best and to make that work for my building. Then very briefly on the concept of negative shaft friction for a single pile in filled up soil. So what means negative shaft friction or down drag? They can develop on a pile shaft when the settlement of the ground that surrounds the pile exceeds the movement of the pile itself. We see that on the little sketch on the right-hand side, the one on the left. So we see that the blue line is the ground settlement. It's bigger than the red line, which is the pile settlement above this neutral plane, where these things are, where the both settlements are similar. It's the neutral plane, and below that, my pile will basically resist that. And so that means above the neutral plane, the settling soil will hang itself onto the pile and basically drags it down. So I get additional loading from these ground conditions. When can that happen? Newly placed fill materials, so reclamations very often, or fill on compressible soil. If I have an embankment of 5 meters high or whatever that is, I have a very soft soil that the soil below can settle due to the additional loading. And if I have piles for bridges, for example, then I can get, or the settling layer can apply down drag forces. Lowering groundwater tables can do that as well. And of course, post-liquefaction settlement during earthquake shaking. So we will introduce an additional axial force in the pile. It's drag force, and this can cause additional settlement. Usually the capacity or the strength is not affected. It's more a settlement problem. So it's an SLS problem because we will increase the settlements. And we also need to consider this additional down drag force in the structural code. For example, AS 15100 Australian bridge code. We have to apply a factor of 1.2 onto my down drag forces, and that needs to be allowed for in the structural design. Settlements, drag settlements should be considered in the SLS assessment. Again, very briefly. And what we can do, we can probably apply bitumen coating in areas where we expect the layers to settle. So we won't get a lot of shaft friction for resistance. But on the other hand, if the soil, if we have down drag problems or negative shaft friction, again, the soil can't hang itself onto it. And we basically almost have a almost neutral section of pile in these layers. We can put some sleeves around it, like we see here. Again, there is no right or wrong. It depends on your project. Sometimes there's a bit of hesitation when we say, oh, if you put bitumen on your piles, if you drive them, particularly in sand, won't you rub it off? Again, I've seen that a few times where when we extracted the piles, they look pretty good. And again, there's no right or wrong, but it's really, as a designer, considering that, thinking about that is very important. Bit of summary of axial pile design. So in your selection include structural and geotechnical consideration, constructability effects, we'll talk about that shortly, and any project-specific boundary conditions. Understand your settlement limits. If you don't understand them, just develop them. You need to know your pile settlement limits. Understand difference between drained and undrained pile design. How reliable are your design parameters, and how realistic? How robust is your ground model? And if you do your sensitivity checks, understand the behavior of your pile foundation. What is your contingency? What if the ground is far worse? Understand that in your design. Pile design strongly depends on local geology and site-specific installation effects. Ensure you assess your risk assessment covers these risks. And again, verification of design through pile load testing may provide considerable advantages, not just for the designer to know, look, my parameters were right and my settlement assessments were right, but also for current design and future applications. All right, if we look at rock socket designs, I've done a lot of rock socket drilling, mainly in Australia. And where we have rock sockets, very often we ignore the resistance of the soil above the rock for the pile design. One of the reasons is that usually the rock provides much higher resistance, but another reason, a more practical one, is the pile needs to move far less in the rock in order to fully mobilize the resistance. So we're not talking about 1 or 2% in rock sockets, it's far less. And this means if my pile only moves a little bit, maybe usually 20-25 mil, this is usually, in my experience, what we allow for SLS settlements in soft rocks at least. But these settlements can be very small and the response is much stiffer. So therefore, the soil above rock socket is really not mobilized adequately. Typically, rock strength controls the skin friction and bearing performance. Therefore, strength is usually used for the design of rock sockets. But if we really look into it, we have to also apply, depending on the project risk, rock modulus and other parameters. The key thing with rock socket design is really to have clean pile bases. If we have debris due to drilling, if the contractor doesn't clean out the base properly, that will not reduce the bearing capacity of the rock because they won't damage the rock, but it will basically create additional settlement. As I mentioned earlier, if you have a layer of 200, 300 millimeters of debris, and then your pile, basically the shaft friction is maxed out and it really goes into the ULS case, So this is when your pile needs to work hard. It's like your life insurance. And then it needs to move 100, 200 mil to compress this soft layer. Ask the structure engineer what they may think about another 100 mil movement, 200 mil movement. So when I went into rock socket design and drilling, told me consider three things really important. The rock socket must be clean, and second is the rock socket must be clean, and the last one is the rock socket must be clean. And this is not just the base there, it's also the shaft. Really, really important. So the roughness of the rock socket is very important. And again, we should think about evidence. So how do we rely on that? If we have a dry rock, we can lower, or we can basically have a mirror and look at it. We can lower cameras down these days. If we have bentonite fluid, there is not a lot we can do. I would not recommend using bentonite fluid for rock sockets. Definitely not, because the bentonite will create smear. And the smear will basically, when you roughen your rock socket, it will basically look like plaster on a wall to make a very smooth socket. And you can reduce your resistance significantly by probably 2 or 3 times from your best option. This is really, really important. Think about the evidence. How do you prove that your rock is really that your rock socket is clean and adequately rough? You're not sure. For some hard rocks, it's not possible. You have to assume smooth resistance, but then you have higher friction values as well because the strength is bigger. Load testing always helps. And the assessment of rock mass modulus, intact rock strength, base friction angles, very important for the detailed design, particularly if we're getting a higher strength rock. That needs a different investigation. People with the knowledge about these parameters, what it means, and it gets more complicated. Looking at lateral pile design, there are some questions. Probably if we wait till the end, if this is all right, they're a little bit longer. If we look at laterally loaded piles, and again, I keep it simple. We rely on a non-linear relationship to provide soil resistance as a function of pile deflection. And very often we reflect that through a series of springs. And basically we will focus on principle of lateral pile design and understanding that these simple methods also contain limitations. And when I look at lateral design, I probably come up with a lot of different challenges because soil strength estimates and my soil stiffness response is not linear. For the axial pile design, I haven't spoken about stiffness. And again, with the simple methods, in my experience, we probably use on 80% of our pile designs. We don't use stiffness, we use strength parameters. In reality, when the whole time when I talk about settlements, we're talking about stiffness. So that's the strain response on when I apply a certain load. With lateral pile design, this is all about that. So suddenly we are talking stiffness, and this is when things getting slightly more complex. Stiffness, soil stiffness, depends on the nature of loading, cyclic, wind, seismic, sustained load cases, depending on my ground conditions. My pile stiffness is not linear, particularly if the concrete pile starts to crack over time. Just microcracking, what reinforced concrete does. The stiffness will change. Consideration of installation effects and dynamic responses of the superstructure, even under light earthquake loading or wind loading or other things need to be considered. This is quite important. We look at limit equilibrium based on Brahms, again, not going fancy, and then soil structure interaction. Limit equilibrium can be very popular, particularly for smaller jobs or low-risk jobs, and we look at the right-hand side. These are the assumptions how your piles will either rotate through the soil as short piles or basically or as a rigid body or longer piles with bending failure of the pile, and this is followed by local displacement. So again, even if we look at short piles that they translate to the soil, it's not realistic. And again, if you think this is not realistic, don't use these methods. Again, for low risk Smaller projects, they may be appropriate. But again, you're just doing ULS checks. With these methods, even though with bronze you can assess your displacements, there are ULS checks. And again, they're easy to use. You can put them in an Excel sheet, and it's very, very straightforward, very easy to use. But the risk, the price for that, the price you pay in your design is accuracy. And they don't really include a flexural stiffness of the pile. And piles don't act as a rigid body. And in order to solve that problem, we should use pile-soil interactions or PY curves. If we look at them on the right-hand side, again, this is from a paper of Rayson and Dave Egan, 2016. Depending on my head fixity, if my pile head is three-headed, like a dolphin pile or pile for power pole, a single pole, it can move freely. My bending moment is somewhere along the pile shaft. If I fix my pile head, and probably 90% of the piles are fixed in a slab or beam, my bending moment, the biggest one, is at the pile head. Smaller bending moment at the shaft. And I can then get these more realistic displacement curves of my piles. Again, it's not rocket science. Again, we can use software like LPile or RSPile or others. I'm not affiliated with one of these software companies. Or what we've done also is doing spreadsheets, and that works as well. You can come up with these correlations and basically build your own PY curves, ideally based on static load test conditions. And again, it's very important doing a sensitivity check for lateral loading for the springs. Usually we use our best estimate, and then you use 50% and then 200%. And we just see the difference. How robust is my model? So when I look at lateral pile design, I usually obtain structure loads from the structure engineers and displacement limits. You don't have any displacement limits for your lateral pile design. It's almost worthless starting the whole process. Probably do a best shot and then say, yeah, look, it's 80 mil. If it's less than 25 mil, in most cases, it's all right. If it's more than that, probably go back and ask for more data. Assess soil profile, soil strength parameters, and then you select your lateral analysis method. Could be limit equilibrium, pile-soil interaction, maybe finite elements. It's worth it. But again, if you do finite elements, think about, do you have the right parameters? Select pile head fixity, stiffness parameters, allowable deflections, and then check if that all lines up nicely. PY method, very briefly, this is pile-soil interaction, widely used. We use it for static and lateral, and for static and earthquake cases. And there, these curves represent the nonlinear behavior of the soil and relates the soil reaction, which is P, with the pile deflection Y along the pile shaft. We see that on the right-hand side. So we have a series of springs, and each spring has their own soil reaction and pile deflection relationship. They're usually non-linear, and they're also a function of depth, soil type, pile dimensions, pile properties, and so on. And they're driven by this reaction modulus EPY, and this is related to the soil modulus and the pile-soil interaction. And that all depends on your limit or on your allowable deflection. So again, if your deflection increases, your EPY modulus changes as well, and you're just turning yourself into circles and chasing your own tail. So EPY is the resistance from the soil at a point along the depth Z of the pile, divided by the horizontal deflection of the pile at that particular point, and that represents this curve at this point. They developed a specific depth, showing soil reaction modulus, and this is obtained by using the secant of the PY curve. And again, you need to know where your deflection is. They influence these curves, they're influenced by pile types, geometry, flexural stiffness of your pile, also type of loading, monotonic or cyclic. In some ground conditions, if you have cyclic loadings, you can double your displacement just by the nature of the load. And of course, pile head fixity is very important. And it's sometimes not easy. It's not 100% fixity or 0% fixity. Sometimes you have partial fixity. And this could be a problem. But again, it depends on your project. All right, if we look at the lateral, a bit of summary, lateral analysis of piles is more complex than the axial analysis. And we can use BROMs or limit equilibrium methods or PY curves or appropriate software if this is available. If we have repeated load applications, they may increase the lateral deflection to about twice compared to constant loading. Very often the soil conditions in the top 5 meters, sometimes only top 2 or 3 meters, are governing. This is why I mentioned earlier, be very careful if you rely too much on cohesion, because cohesion may change. Addition of water or anything else could change, make your soil softer, reduce the stiffness of your spring, create significantly more deflections. Don't say ignore it, but just caution. And again, if you put in your design a high cohesion value, you may get fantastic deflection values very low, but the thing is, if it's realistic, that's the next question. And then maximum bending moments for fixed-headed piles are typically located at the pile head, and bending moments for free-headed piles are located along the pile shaft. It's important to look at the construction site and to see if the crews who build the piles, if they really follow your method of providing fixity or non-fixity. Because if you design your pile with a maximum bending moment at the pilot and then the pile doesn't have fixity, your bending moment will be at the base and your reinforcement may not be adequate. So this is really important. All right, let's talk about conventional pile construction. So speaking about board piles, where we basically we're drilling a hole and filling it with putting a reinforcement cage in and filling it with concrete. We can leave steel casings like we see on the right hand side in the ground permanently. For marine piles, that's very appropriate, and rarely in other occasions. Because for marine piles, if they stick up above the seabed, the casing is at the same time kind of formwork for the concrete. Sometimes we have permanent casings that we can take into account for the design, or we can leave the casing in the ground, and it's called a sacrificial casing in my part of the world. And then they said, yeah, you can have it, but you can't take it into account for the design because it may corrode over the design life. If we, in some instances, we don't need to leave the casings in the ground, so we need short starter casings. Very often we use that in combination with drilling support fluid. So we have a short starter casing, drill the pile, excavate the hole, top it up with drilling support fluid, usually bentonite, polymer, in some occasions water. Drill to the base, clean the base, install the cage, pour the concrete. So with board piles, we always, or piers, well, they're called in the US, or drilled shafts. We drill a hole first, inspect the hole, inspect the cleanliness of the base, then we install the reinforcement, and then we pour the pile. Extremely flexible system, up to 3 meters in diameter. I'm just reviewing the final design for Big Bridge in New Zealand, where we used 19 3-meter diameter monopiles up to 35 meters deep. Yeah, they can be small as 450 millimeters. Very, very flexible, very good capacities, lateral capacity, bending capacity, can be installed with limited noise and vibration issue, usually higher load capacities than driven piles. We may need increased quality assurance and inspection, particularly to verify the ground conditions. Storage space for pile reinforcement, insufficient base cleaning may cause reduced capacity. And we may need temporary support like bentonite or polymer. Question, there's talking about loss of pile loading capacity due to poor slurry control or pure base cleaning. What is your experience with loss of pile capacity due to time delays? Oh, that's a big problem. End of drilling and start of concreting. Don't have any literature references about that. Just developed the New Zealand piling standard is currently under public review, but we usually say 24 hours between cleaning or basically opening your socket and finishing the pile. There is no real, it's very tough to say, look, do we have the parameters if we have 48 hours? I would, yeah, again, it depends. It's usually anything between 50% and maybe 75, 80. Depends a little bit on the risk as well, depending on the design. And this is when I recommended sensitivity checks and say, look, what if your parameters half? Does it mean you have to drill another meter long or another 2 meters longer? So usually it's extending the rock socket if that happens, and you extend your pile length. But this can be very, very tricky, and this is a very, very good question. Don't have any literature references. Maybe I think there are a few piling standards they make reference, but they don't tell you how much reduction is required. And again, I would always go to a sensitivity check. Look at my rock socket and say, what if I probably halving the resistance, depending on your strength, is probably a little bit unfair. It's probably a little bit too much. But again, if you have mudstone, you can easily halve that. There's not an easy answer to that, unfortunately. What can be done is just waiting and then drill the pile, case the pile, and the next morning drill the socket, and then they should install the cage quickly. In clays, it's probably more critical than in sands, because with clays, if they're in contact, if it's polymer, it's probably not so bad, but if they're in contact with bentonite or water, they can turn into 10 kPa strength soil, so really expect the worst. And we've done a few load tests in Asia where we expected dense gravel, and then the bentonite basically had a film, and it was exactly that problem. The pile was open for too long, almost a week, and we said, look, we do the test anyway. We did the test, everything was set up. There were problems by the contractor, and we got back analyzed 10 kPa shaft friction in gravel. And you say, what is that? And then we basically concluded it's really the bentonite clay built up between the concrete and the soil. So basically you created a slip surface of very soft clay. This was an extreme example, but it has significant effects. For 2,000-ton dynamic test, how much drop energy on pile can be considered a proper pile settle result. Rule of thumb, we will talk about that later. Whatever your test load is, 2%. Your energy should be about 2% of your test load. So if you have 200 ton, for example, 200 ton, 2%, 4-ton hammer roughly. Classic here is about the limit for load testing. Dynamic load testing is about 1,000 ton, so you get about 20 ton drop weight. And this is when you start damaging your pile head as well. But roughly, they say 1 to 2%. I would always lean towards 2%. Use of temporary casing. Do we need to reduce skin friction coefficient? No, we don't have for temporary casing. For permanent, I will talk that in a minute. But for temporary, because we extract it and the concrete will be in contact with the soil again. All right, favorable ground conditions, basically everything other than very soft soil and contaminated soil. So board piles are very, very versatile. Drilling support fluids, and we will talk about polymer, bentonite, and water in a minute. Just checking base cleanliness, and there are some measurement devices where you basically have your tape measure and put a piece of steel, could be a plate or a piece of reinforcement at the end, and then you basically tape it. And you basically, when you reach the base, you will find that it stops, and from there onwards, it may sink in. And depending how much it will sink in, you can then get, usually we limit it at 50 mil, because we think when we place concrete with the Tremie method, 50 mil of base debris is enough that the concrete, when it flushes through the Tremie pipe, that it will flush the pile base, and it will be in firm contact with the soil. If it's more than 50, probably some of the debris will be in place, particularly in the corner sections of the pile, and that may cause a problem. And usually we tap at the 4 quadrants and the center. And yeah, so that's in accordance with the specification, with the spur bar or spur wall specification for piling and embedded retaining walls from 2017. All right, if we look at excavation support for board piles, very often we need support. Permanent steel liners, temporary steel liners, or drilling support fluids in combination with temporary steel liners. So we also need to think about how do these casings affect my design. For permanent steel liner, the shaft friction of the pile along the case portion may be reduced or ignored. We work for some road and traffic agencies in Australia where they said whenever you're the casing, you can't allow anything, and others say 100 kPa. So there's not a lot we can do because it's the client. If we don't like it, we have to think about something else. And this is quite important. Some drilling fluids also can reduce the shaft friction resistance, particular bentonite and water in clay. A few words about permanent steel liners. In some instances, if we have steel liners and we have to penetrate harder layers, we need driving shoes. So these are basically welded steel sections to the base of the casing, which are thicker. My casing may be 16 millimeters and my shoe may be 25. If my shoe encroaches to the outside, so that basically it's slightly thicker than my casing, contractors will love it because you drive it down, you screw it down, it will break the skin friction. And because the shoe is bigger than the casing, there will be an annulus, no skin friction. We can install it easily. If I keep the casing in the ground, it's a nightmare because I have zero skin friction. And this is the key thing. For the design, I want the basic driving shoe encroaching to the inside. If I want to allow for any resistance, contractors may not like it because they may say, no, if it encroaches to the inside, my drilling tools may get stuck. Please specify that if you design on the drawing. This is very important. And I've seen jobs where we had to disregard 20 meters of skin friction. And of course, the pile was under design and it was a nightmare. So we had to install additional piles and all other things. We then look at drilling support fluids, and we will talk about bidirectional static load test towards the end of the lecture. Foundation embankment dam, or it depends, depending on the soil type, driven or board pile. It depends really. There's no, I've done both, and it's usually a price thing. And yeah, they both work. Particularly if you use drill displacement piles, you get the effects of the driven pile, but not the noise and vibration. Usually, whenever you can use driven piles, they should be cheaper than board piles, but they come with a price with noise and vibration. Drilling support fluids, depending on ground conditions, what support fluids we can use. Installation techniques, drill tools, again, the fluid itself, use high quality fluid if possible, and performance criteria of the structure. The key thing for any drilling support fluid is we need to apply a positive pressure head. Rule of thumb, at any time the fluid must be 2 meters above the groundwater level, at any times. If it only drops temporarily below groundwater, a few seconds may be enough and your sand or something will cave in and then you have a big problem. So this is the key thing. We can use water bentonite polymer. Water is rather rare. We use it when we basically drill our casings into the rock mass, embed it, provide a seal, then we drill the rock socket uncased. And with water, you can clean your rock socket. That's the best thing. Some water may seep through the rock, or if you have marine piles, water will penetrate. But this is usually the case. Bentonite is a mineral slurry, so it's basically clay powder. We have to mix it with a high shear mixer. Let it hydrate 12 to 24 hours. And then the bentonite, basically with a 2 meter pressure head inside the pile, it will apply pressure onto the formation. If it's sand, for example, some of the bentonite will disappear in the sand, but because it has these hydrated clay particles, they will block the voids in the sand very quickly. And then there will this buildup of filter cake inside the pile. Depending on your bentonite quality, this may be thin or thick. You want to get a very thin one. And then your borehole is open. And bentonites work best in gravels and sands. Bentonite needs to be circulated and cleaned before concrete is placed. If there's too much or more than usually 4% sand content, could be 2, could be 4, depending on the standard you're using, you may get inclusions on your reinforcement, and that's a very nasty defect. They don't work in clay because clay on clay, or the clay will swell. There are a lot of free water molecules in your bentonite, and this is why they invented polymer, or they found that polymer works well in clay. If you have clayly soils, use polymer. Polymer works differently. Polymer, all the fines will be settled to the base, and the contractor needs to come back with a cleaning bucket and excavates them. Bentonite, you have to clean your bentonite fluid outside of the hole, pump it out, bring it to descenders, and clean it there. So much more cost, much more time. This is a bit of a summary of what I just mentioned. Bentonite suitable for sands and gravels, keeps the sand in suspension, but you have to pump it out and clean it externally. Polymer, most suitable in cohesive soils, and that basically fluctuates all the fines within 20 minutes, 30 minutes to the base, and then the contractor can clean it. You can do your base tapping. All right, so what are the effects? We have 25-meter gravel filled on the jetty on a seaport. What is the best way for board piles? I would say line piles. Whenever I see seaport, and if they're in water, probably line board piles. But it's very difficult to give some advice without knowing more details about the job. But usually for marine jobs, very often the piles are cased or permanently cased. Just an example to show what I meant with sensitivity and robustness of the design. So if I have my board pile in clay, for example, and my best estimate is 35 kPa shaft friction, 10 meter long pile, 450 mil in diameter, base resistance 3 MPa. What about the shaft resistance? That's my best guess is the red line. What if I only lose 5 kPa, or if I gain 5 kPa? For example, if my ground is slightly worse, probably you would say nothing, Martin, because look at the ULS. You still get for your red line 800 kilonewton at 45 mil. That's about 10%. So this is a really low test. If it's only 30, so the black line, you get 740. That's not a lot. The blue line probably around 860. Not a big problem. And you're right for ULS, but what about SLS? And this is the problem. For example, if we have a bentonite filter cake, then we may get the problem. Depending on my load, I look at 500 kilonewton, my settlements increase from 5 to 9 mil. You may think, look, this is nothing. It's almost 80, or it's 80% increase. For 700 kilonewton, it moves from 22 mil to 36 mil. And this is what I mean with robustness of design. If you only lose 5 kPa in this particular example, in this particular case, you're in big trouble, not in your ULS, but for your SLS case. And this is what the structure sees every day. And you rely on shaft friction. And this is the problem. Probably a lot of the load will then be taken by end bearing. And this is what triggers the additional settlement. And this is why it's quite important to also look at your settlement and your SLS behavior. It's a bit of a table about suitability of water, bentonite, and polymers in different ground conditions. And there's also the guide to support fluids for deep foundations from the EFFC and DFI that can be used. Just a slide about rock drilling of board piles. One way of doing are these brushes, and particularly in high strength rock where you have the risk that your drill spoil may basically block your roughness of the rock socket. This way in dry holes may work very well. All right, a few words about concrete. My work as an independent expert, I came across probably 80% of all piling defects are related to concrete. It's not so much about drilling, it's about base cleanliness, but probably, or let's say 1/3 base cleanliness, roughly 2/3 concrete in a nutshell. And of course, there are the special cases. Why is tranny concrete more different? Board piles can be deep, and the concrete inside the hole, when it's filled, particularly with bentonite or polymer, I will fill it up from the bottom up. So that means my first concrete I pour in the hole will always stay at the top, and it has to rise upwards slowly, slowly, slowly. How long the pour will take, this concrete needs to be workable. Concrete is also subject to high pressure. So basically, when I have a 20-meter deep pile, due to the self-weight, the vertical stress the fresh concrete will apply on itself, basically close to the base, could be up to 5 bar, 500 kPa pressure. So that needs to be considered in the design, needs to be self-leveling, must easily flow around reinforcement bars, and also must achieve bond with the bars. And we talk about workability and stability. And workability, pretty clear that it needs to move rather quickly laterally in order to flow through the reinforcement cage to fill the cover zone. Stability is the resistance against segregation mainly. The concrete is too sticky, so if it doesn't work very well, the lateral flow is blocked, and it may not flow through the reinforcement cage, particularly the top 5 meters, where you don't have this concrete pressure head. You may end up with some issues in the cover zone. I've seen that a lot, and it can be a very, very painful exercise because your durability is not given in this section. And how do you assess how deep down it goes? And again, congested reinforcement can be a problem. Sometimes it's just easier to increase the pile diameter a little bit, increase the spacing of your reinforcement a little bit. Even though it's a higher cost in material, it's probably just a fraction of the cost if you have to investigate any defects and redrill piles later on. Usually we say we need concrete fines, and I did a lot of research on that, 25 to 30% of fines passing the combined grading curve at 600 microns. Very often this is forgotten. It's really, you need your fines, not too many, but not too little. If we look concrete bleeding in board pile, that's a nasty bleeding channel. This is when the concrete doesn't hold up, and when you basically pressurize it, the water moves upwards and basically washing a channel to your concrete. Very often they rise up along the reinforcement bars, and that's a problem. There's a filtration apparatus, the Bauer filtration test. Basically a little steel tube, you put your fresh concrete in, put a lid at the bottom, has a little hole, then you put a lid at the top and apply pressure. Usually we say 5 bar for a standard 20-meter deep board pile. Leave it there for 5 minutes, and then we measure the amount of water that drops out. And based on that water, there are some correlations based on your Tremi concrete guidance, where you said that's acceptable, that's not acceptable. And then you open this cylinder and pour it in a bucket, and what you see there is basically 300 millimeter, 1 foot high stiff concrete. Imagine this is how your concrete looks like at 20 meters depth. You think it will flow through reinforcement cage? Probably not. What's the slump of that? Maybe 80, maybe, I don't know. But it's certainly not ideal. So if we look at that, I come back to placement in a minute. But there are a few best practice documents. So the first one from 2012 was Tremi concrete for deep foundations. I was involved in the development, came back with a few simple criteria. Actual slump flow is basically the time it takes for the slump. You lift the slump cone, how long does it take for the concrete to stop flowing? We said less than 5 seconds ideal. It needs to be quick. We tested 50 different tests, mixes, all with 230 mil slump, and we had significant differences. And there's the other one, the Guide to Tremi Concrete for Deep Foundations from the EFCC and DFI. The latest revision is from 2024. We released it in December. Much more detailed, more tests, very good background information. Sometimes check if the specified tests and if they're available in your region. If it's a more rural job, they may not be able. So again, this is why I sometimes prefer the Australian, much simpler. But again, this is a great document. If you want to learn about Tremi concrete, and download it for free, and it's a good read. Then for placement, this is a Tremi pipe. You basically put it in your pile that is filled with fluid to the base, lift it up, and have a separator basically cast your concrete. have a rubber ball of vermiculate at the top, and then your concrete pushes it down to the tremie pipe, and all the fluid that's inside the pipe will flush the base, because the tremie sits about a foot above the pile base, so flushes up all the base debris, ideally up to 50 mil. And then the concrete is placed and rises up, and then all this stirred up base debris will settle on the top of your concrete, and if you move upwards, it will stay there, and this is why you have to trim it back. They usually say about 300 to 500 mil contaminated concrete. So that's quite important, and probably these documents will inform a lot about tremie concrete. Quick summary of board piles, very versatile, can be installed with limited noise and vibration. Base cleaning is critical. When we use drilling support fluids, always maintain a positive pressure head. Very briefly, of continuous flight auger piles, not sure how popular they are in Pakistan. We see a rig here. It's basically another method to install a board pile. Rather than drilling fluids or casing, we use a hollow continuous auger, which the sacrificial seal we drill in the ground. Then at the design depth, we just swap to concreting and basically pump fluid concrete to the hollow stem, lift the auger, and then we plunge a reinforcement cage in. Biggest risk is the plunging of the reinforcement cage. If it gets stuck, you may have a problem. If it's halfway in and you need a full-length reinforcement cage, you have a big problem. Very efficient, much quicker than board piles. You don't need casing, you don't need support fluid, minimum noise and vibration. Advantages is limited in depth and diameter. Spoil removal, think about that. Long reinforcement cages may be hard to install, and advanced concrete technology is required. If my penetration rate is too low, I may have over excavation. So that means like that, my auger spins without penetrating in the soil, basically flows inside my auger sideways. Particularly if I have an adjacent building, I may cause settlements, but I also reduce the strength of my soil in this layer. So that's one of the biggest problems. TFA piles are normally fully monitored. There are computers on in the rigs. They show you, the penetration rates, the drill torque, the concreting rate. So it's very important QA document, because you don't have the opportunity to inspect the hole. It's a blind process. And as an engineer, I couldn't say when the reinforcement cage sticks out of the ground if the pile is 2 meters or 20 meters deep. I would not know unless I do testing. But yeah, so that's quite important. Applications, retaining walls, foundation piles. If you do secant piles for shafts or basements, guide walls are required. I would never ever install a secant pile wall without a guide wall. See an example on the left-hand side. When the piles kick out, they don't overlap. So you need secant pile walls for shafts or basements if you have high groundwater levels, mainly for groundwater management, or achieving a certain waterproofing performance of your wall. If your piles kick out, you won't have that. And I've seen horrible things during my career. Concrete, basically you need to spread concrete, very flowable, ideally. And then on the right-hand side, you see the crew just pushing the cage into the fresh concrete. They are basically concrete board piles. Yeah, with special requirements for concrete, and I'll probably go back. So basically we need, that's the last bullet point. We can use slump concrete, but then it should be 240 mil slump, really workable. Ideally, what we use in Australia and New Zealand these days, 550 to 600 millimeter spread. T500 time 5 seconds, or whatever, you lift your spread cone and it should stop within 5 seconds, because otherwise you can't plunge your reinforcement cage. I normally use 4 hours retardation, but again, that was just me when I worked for contractors, because I wanted to have this contingency, particularly if the concrete is inside the hoses, inside the rig in summer, and if there's a delay in concrete supply and the concrete goes off in the lines, that's a nightmare. All right, very quick, very fast installation. There are board piles. You achieve the same pile as with standard conventional board piles if carried out correctly. Suitable for medium bending, so they are limited in diameter and depth. Probably depth, let's say maybe 15 meters, 20 meters, and diameter usually 900 millimeters, sometimes 1200. And we need advanced concrete technology. All right, a few slides about driven piles before we get into pile testing. Driven piles, they are usually cheaper than board piles. Wide variety of materials and shapes, better quality control for structural strength, little spoil for removal and disposal during installation, and they may increase the soil around the pile during driving. We need a bit of advanced planning, allow for stresses during transport and installation. Specialized splices may be required, and we will have noise and vibration. There's no way around it, unfortunately. They're suitable basically in all types of soil conditions, weathered rocks with short sockets, and of course below the groundwater level. Unfavorable in high strength unfractured rock, we will just break the pile. Soil conditions with obstructions, and sometimes we can use driving shoes to penetrate harder layers. In general, all types of structures can be used, very often for marine piles, for bridges, for buildings, ranges from as small as 450 to 250 mil in diameter for steel piles. Very, very different applications possible. We can do raked piles easily. I've done 1-in-1 piles for some marine jobs, but very, very versatile. Drivability analysis is very important. So if we have excessive driving stresses, we may damage the pile head or bottom. It's not always possible, but we should think about the hammer selection, and a bigger hammer is the better solution. Early on, I mentioned 1 or 2% of your test load or your ultimate driving load. That's a good selection. Select your driving criteria. We'll talk about highly formula in a few minutes, or PDA testing or dynamic pile testing. Define your refusal level. Usually we say 2.5 millimeters per blow or 25 millimeters over 10 blows, averaging it out. And that's quite important. We can use hydraulic hammers, drop hammers, air hammers, and diesel hammers. So there's no right or wrong, whatever is available, and they're just providing the energy. What is more important is to understand that we're talking potential energy. That's the theory, whatever my drop height is multiplied with my weight. Then I will have losses due to the drop. And this is my kinetic energy. And then when I have a cushion on top of my pile head, so that the hammer doesn't break the concrete, for example, I will have losses in the cushion and the helmet, and then I have my transferred energy. And depending on my hammer type, if I have a hydraulic or drop hammer, my effective energy, my transferred energy can only be 60%, anything between 60 and 100%. Some hammers, they drive steel to steel. Hydraulic, brand new hammers, usually they're around 80 to 95%, but they can be as low as 60. For steam and air hammers, 40 to 70%, diesel hammers with 30 to 60, and rope-driven hammers between 20 and 80%. And this is the biggest problem. They are not constant energy inputs. It depends on your hammer type. It depends on your friction. And with your highly formula, which turns 100 this year, it's been around for a long time, a very, very useful method. It's a verification tool. It's not a design formula. You basically, in the first bracket, you have your energy. It's your hammer weight multiplied with your drop height. And then there's the efficiency factor. With the efficiency factor, you can go wrong unless you measure it with PDA testing. And then you can basically correlate a site-specific relationship for a site. And then you divide it by your set and half of your temporary compression. Your temporary compression is basically your pile bounces back, and the set is how much it penetrates permanently in the ground per blow. So your temporary compression is usually the elasticity of the pile, elasticity of the soil. So it's called the quake of the soil. Yeah, these are the main components. We want to talk about pile setup. So in particular in cohesive soils, if you drive piles, you have an excessive buildup of pore water pressure, because when your pile penetrates, your pore water can't escape quick enough. So you may get very high pore water pressure. And that will decrease the shear strength of the pile. If you drive your pile in clay and you do, for example, a dynamic load test the same day, you will not get your final design strength. Very, very unlikely. And this can cause a lot of problems, a lot of irritating questions from the client and phone calls and stuff. So you have to wait, ideally for 2 weeks, depending on your ground. If it's plastic clay, 2 weeks. If it's a sandy clay, maybe a week. For another soil, maybe two days. But you have to do a restrike, test it again. It could be highly, it doesn't have to be PDA. But if you test it after a few days or a week, take your first few blows, don't redrive the pile, because then you increase the pore water pressure again, then you have the same problem. The first few blows, you will find that your setup effects will give you a much higher pile resistance. Pile driving records, ideally, they match the SPT. So we see that here, number of blows, the blue one is my driving record, the black one is the SPT, and they follow it nicely. So I can see when the resistance gets high, I'm getting closer to my foundation level. And that's a good thing. All right, summary, noise and vibration effects need to be considered. They are an issue potentially. Selection of pile driving hammers is important. Setup effects to be considered. Again, end of drive, particularly in clay soils, it's unlikely you achieve your resistance. In some instances, the client says, no, we can't afford that. We have to keep going. Then do load tests or do your highly formula, and you basically over design your piles, because they can provide maybe 50 to 80% of their initial resistance after end of drive until the setup occurred. Predicting of setup is very, very difficult. We use ranges between 1.2 to 2.5 or something like that. So how long is a piece of string? It's very important to assess unless you measure it. All right, I know we probably have only 15 minutes to go. A few slides about integrity testing and load testing. So pile integrity testing is quite important. We see a few defects, a few damages here. We don't want them. But what integrity tests can we use, and what can we assess? So the first one is the low strain integrity test, or hammer pulse technology. It's non-destructive. Hammer impact method. So we basically have a small hammer, we have a geophone, we hit the pile, and then we send a compression wave down the pile with a handheld hammer. Wave travels down the pile shaft and will be reflected when we have a change of impedance. For example, the interface between the pile toe and the soil, if there are any cracks or if there are any changes in pile diameters. Provides a graphical display, velocity records, and usually we take 3 impacts and they're averaged. Never go settle with one. We want to have an average. Optimal, or was developed for piles up to 1.2 meters in diameter. We've tested 3 meter piles, but again, this is the optimal range. For slender piles with a length to diameter ratio less than 30 and in stiff to medium dense soil. This is where it works best. It also works in other conditions. Preparation of the pile head is very, very important. You see on the right hand side, it's a really nicely prepped pile head. If it's not, you may get results that may not be reliable. All right, this is basically how it looks like. The blue wave is your compression wave. Hit it with a handheld hammer, travels down, gets reflected. And then you can assess your time. T0 is the starting point, and 2 times L divided by C. C is basically your wave speed for concrete, very often in the range of 3,500 meters per second. And then you basically get your upward wave. So this is the theory. You get these little graphs you see on the right-hand side, and this is for fixed-ended piles. So for example, a pile sitting on a harder foundation layer. You send a compression wave down. This is a prefabricated pile. So you have a beautiful diameter, and it's basically almost a straight line. And then you get the toe reflection. In this case, it's a tension wave. And this happens when you basically sit on a fixed foundation layer. If your pile moves a little bit, or if it's the same material, if it's not a stiffer pile, if it's a free-ended pile, you get a compression wave back. But again, this is the optimal theoretical line. Or if you have a prefabricated pile, steel pile, or a precast concrete pile. For a cast-in-place pile, a board pile, that could be your soil response. It's not too bad as long as you get a reasonable toe response. So this is basically PIT testing, or low strain integrity testing, or the hammer pulse method. If we have defects like cracks, my wave may be deflected because it can't penetrate the crack, and partially basically it can get along on the left-hand side, but it will also be reflected. So if we look at the right-hand side, some parts of the wave go down and another one gets reflected. So we get an earlier signal. We get a signal that gets higher up. And in reality, that looks like that. We say, hang on, that's half of the pile shaft. We're getting some kind of response. And I call it anomaly. I wouldn't call it defect because we don't know what that is. But then we can do coring or other things to further investigate these things. And that's a relatively straightforward test, relatively easily. And the question is, what can we identify? So understanding the limitations of the test is very important. So on the left-hand side, an issue with a concrete cover. That's what I mentioned earlier. When your tremie concrete doesn't flow laterally, it can't squeeze itself through the bars. Looks like that. PIT testing can't identify it. The one in the middle, it can, because there was a pretty ugly void in the middle of the pile. This pile was driven onto rock, and the contractor kept hammering. The pile was crumbling at the base, but was going at the top. So I said, oh, what do you want? It works well. And then we tested it, looked horrible. And then we checked it out. It looked like that. And the one on the right-hand side, the bulge was identified. It's not a problem. It's just more concrete. But for our application, it worked. All right, just application. It's an indicative assessment of necking and bulging and identification of severe or major defects. Full diameter cracks, large inclusions. We can't have a detailed assessment of necking and bulging, and we can't have an assessment of the pile diameter, and any minor cracks or inclusions may be missed. If we have rock sockets where the rock has the same specific weight or the same stiffness as my piling concrete, for example, the signal may just disappear on the rock and we don't see a toe response. We have that a lot in Auckland and New Zealand, where we rarely use PIT testing or we use it to assess the integrity of the pile, but not the rock socket assessment. And it's really there for locating major anomalies. To match N values, you showed how much energy of impact hammer was used, 90 kilonewton. Not sure what it's related to. The last one, how do you see conducting thermal integrity test over sonic logging test? We'll talk about thermal integrity in a few minutes. It's relatively new. We don't understand everything. We understand a lot. It's a good alternative. I'll talk about that in 5 minutes. Another test is crossover sonic logging. For example, for board piles, if the pile diameter gets bigger, we use crossover sonic logging. It's also non-destructive. And we attach tubes at the inside, 50 millimeter tubes at the inside of the reinforcement cage, install the pile, pour the pile, and then we fill these tubes with water, and we basically lower probes down, one receiver, and one sender, and then we basically do a cross-hole sonic log of the pile shaft inside the reinforcement cage. Usually 600 millimeter diameter upwards, otherwise it gets too congested, you can't get your tremie pipe in, and you want to have at least 4 tubes installed. And then you measure basically the time between the pulse generation and signal reception. That's your first arrival time. And you measure the strength of the received signal. So if there's a whatever bentonite inclusion in between, your wave speed is different. It penetrates through the concrete, then through the bentonite inclusion, and then through the concrete again. And you also lose energy, and you will see that. There's a risk of debonding, and this is why you usually use, we would prefer steel tubes because of the coefficient of thermal expansion. And all these tubes need to be filled with water straight away. Ideally, we flood the pile head before testing because sometimes the concrete debonds from the tubes, particularly in the top few meters. If there's air in between, we will get funny results, and if there's water in there, it helps with the wave transmission. So this is how it looks like basically. On the right hand side, we have the transmitter and the receiver, and we have the transmitted signal, transit time, and the received signal. On the middle side, we see our arrival time, really a nice straight line, no issues there, and our energy, a bit of zigzag, but not too bad, really looks all right. Sometimes we see indication of the potential defect at the top. All right, this is basically, we have 4 tubes from the tube at the top to the tube on the right hand side. We see this, there's a significant disturbance. We call them waterfall diagram. At between 16 and 18 meters, something is going on. If we further investigate that, large deviation of more than 20% of the first arrival time, 20% less, and my relative energy drops at the same time by about 50%. We said, all right, we have to do concrete coring, and we detected an inclusion at the inside of the pile caused by bentonite inclusion. So bentonite fluid wasn't cleaned properly, and that was a problem. And then there's this rating guide. If I, for example, more than 20% based on these diagrams, I can then go back and say, what is my rating? Category A, no significant defect. So that means if my first arrival or my relative energy is between 0 and 9 decibel, whatever this thing measured, and my first arrival time is within 50, or the first arrival time losses, the delay is less than 15%. I'll go to the yellow one. Depending, my relative energy reduction can be higher, or my first arrival time. This could be minor defects. Consider the depth location, rule out debonding, so flood the pile head again and retest after additional weighting. If it still doesn't work, it may be category C. Then we have to excavate if it's near the ground surface. We have to do some core drilling, maybe do another PRT test, and maybe, repairing defects or replace the pile. This is when it gets tricky. And again, if we look at different defects, and again, any defects in the cover zone can't be detected with this method. This is critical to know. So we wouldn't see that. We do the test, and then we dig the pile out, we see this, and the client said, oh, why did I pay so much money? Because that's a test limitation. Identified the middle defect with or the second one from the left was identified. The big void inside the pile was also identified because it was located within the reinforcement cage. But on the right hand side, these bleeding lines between the reinforcement cages were not detected. So we did cross-sonic logging because the tubes were installed inside the reinforcement, wasn't detected. If we would have installed them outside, the steel reinforcement cage would have been an obstruction. So this is a significant limitation because we only measure the concrete inside. It's only an indicative assessment of necking and bulging. Then weighting is quite important. So day 1, 2, 3, and 4, and it was a high-rise building job. The client pushed us and test after the first day. It looked horrible, lots of energy losses, but the concrete needs to harden and gets the final E modulus. So we saw after day 4, it looked better. ICE and AS2159 proposed to wait for at least 7 days. Not sure about the American standards, but yeah, it's give it 7 days. Thermal integrity profiling is the last one I want to introduce. Evaluates the concrete cover inside and outside the reinforcement cage. We can evaluate as early as 12 hours after concrete placement. And what we do, we measure the concrete temperature. So we have little thermocouples along the reinforcement cage, and we get this temperature profile. And it's very, very useful. For example, if we have any inclusions, we have 4 thermometers and we have an anomaly on the left-hand side at T4. We see that the temperature at this depth at T4 changes. And then we can say, oh, there may be some issue with cover zone or something like that. So again, this is a new technology. Just used it on a recent job, a bridge job. And it evaluates concrete quality and cover. Usually we have to do the measurements during concrete setting. We can assess the shape of the pile shaft. It detects significant defects across the pile shaft, and most cost efficient. It's really, really cost efficient. And there's no risk of debonding of the pipes, and contractors like it because they don't have to attach all these tubes. But the method is new and has limited track record globally. Probably in the US, they've done the most. Australia, they have done a few, but I think the rest of the world tries to catch up. There's a lack of international publications. You know, what happens if your concrete temperature is 63 degrees for one part, for the other one, it's only 58. How do we deal with these things? We need pre-planning. It also won't detect small defects, and testing is only possible during early curing. We can't revisit it. We can't say, oh, we do another test because we found an area. We have to do then coring or other things. And again, it may not be available in all regions globally. Bit of a summary: with all these testing methods, we only can assess major defects. TIP may assist with concrete cover in particular. They're all pretty robust and really suitable to detect major defects, but not really good in assessing small details. I think I'm not sure how we run with time. We should take some time for questions. Otherwise, I'm happy to go through a few more slides with load testing. What is the preference?
Dr. Martin, if you can finish it within 2-3 minutes, you can go ahead with pile load testing. Otherwise, we are very tight with the time now. 2-3 minutes,
right.
if you can, please do it.
Okay, I'll wrap it up. Pile load testing, basically, we want feedback from the pile designer, for the pile designer about load displacement behavior. We spoke about strength reduction factor. And there are different tests. We can do static testing. It's very slow. And we actually measure the displacement. We've seen static load testing curves earlier. And we can also...
Please keep your microphone muted, please.
Now, इसलिए नहीं जा रहा है, पीछे से मेरी कुर्सी का नजर आ रहा है तो कहाँ
I don't know who is. Ladies and gentlemen, please keep your microphones muted. Yeah, go ahead, doctor.
Thank you. Can be smaller static load tests. There are lateral static load tests as well. And one slide about bidirectional load testing. We basically cast the hydraulic jack into a sacrificial test pile, and then we basically lift them up. So we see load displacement curves like that. So basically, we put the load cell at this middle point where we have the similar amount of resistance above the load cell, mainly shaft friction, and then below as well. We get these load displacement curves, and it takes a lot of experience to interpret them. Another risk is they are very expensive. I've seen a few, and in all cases, the designers took parameters that were too conservative. So the load cell was too small. So we ended up at the not even at SLS load. There were barely any movements, and the client was furious because they paid a lot of money for that. So again, horses for courses, for loads bigger than 20,000 kilonewton per pile, this is the only reliable method do a pile load test. But again, it can be very difficult to interpret, and they're very expensive. Yeah, dynamic load testing, probably just explanation, not too dissimilar to PIT testing. We hit the pile with a hammer, then we mobilize it probably 2 or 3 millimeters, and then we send this compression wave down. It will be reflected, and with this reflected wave, we get basically force and velocity data, and then we can put them into CapWeb, which is a signal matching program, and then basically we get these load displacement curves. So we are basically transforming a dynamic pile resistance into the static resistance using CapWeb. So a PDA is basically just a data collection process where we hit the pile. We're interested in the upward wave, and then we put that in wave matching, and then we can get an estimate. This is the biggest difference. Dynamic pile load testing is an estimate. It's very accurate if the pile or the interpreter is experienced, but with static load testing, we get a real number. We apply a real load and get a real measurement. We also can test load board piles, I said testing frame or hammer weight, about 2% of the test load. And that's basically it. That was 3 minutes. Apologies, I had to rush through the last few slides a little bit. But that's basically the end of the lecture. And there's probably some time to go through the questions. How do you see conducting thermal integrity tests over sonic? I think hopefully I responded that. It's another method. It's probably worth it. Maybe combining it on a job to help to get more data. I have 3,000-ton load test with Kentlich platform. That could be a record for static test. I don't know. It's a big test. Congratulations, but it could be a record. And I know in Singapore they probably will claim they've done more, but I haven't done a lot of Kentlich, but it sounds like a fantastic test load. We went through it. I go from the bottom up to match N values. You showed how much energy impact hammer was used. Or with this, I don't know. That was just an example from a job, but again, it's worth correlating that on a project-specific basis. So that was just an example, and special consideration.
I think you answered most of the questions. Let's go at the top. The question is from Miss Kin. She's asking for cohesive soil with high permeability, including fine particles, tight pores. Can we reduce seepage of the foundation for supporting pile foundation as ground improvement? Single pile or group pile, which is more effective? Let me know.
Oh, great question. With high tight pores, can we reduce seepage? Yes, we could. Or there's Australian piling standard AS2159. They have certain exposure classification for sand and for clay, for cohesive and granular conditions. And this is quite, that is probably helpful. Not sure if we can. I think we would consider the group pile if it's usually spaced within 2.5 times the diameter. Depending on the method, in sand conditions, for example, if we over drill, we may loosen the soil, so we may increase the permeability. But if we have clay, it's probably reasonably constant. It's a tricky one without knowing more project specific details.
Up there, Sohail Kibria has asked your commentary on the selection of NQ parameter in various ground conditions for drill shafts. He's asking about NQ parameter.
Yes, they vary. They vary from standard to standard, and it's a big frustration. They can be very low. They can be too high. If they've been measured to be too low, it's probably a costly problem. If they're measured too high, you get an unconservative pile design. What I I would probably go to the limiting values, and this is another way of doing it, and say, look, on the Poulos paper or other publications, if I have a medium dense sand for a board pile, I use 4,000 kPa, and then I do an assessment and say, what if I reduce it to 3,500 or 4,500, rather than using the NQ correlation. And yeah, I found this way a better alternative.
Okay, now there was a question from Sohail Kibria. I know it's a bit complicated question. It might take time. If you can answer it quickly, Dr. Martin, your comments on the ASCE pile load test interpretation criteria.
Oh, this is probably takes longer. Again, it's probably too complex for a quick answer. I think generally speaking,
I can understand.
yeah. Sorry. If I only
I can
say one
understand.
thing, I'm missing the other. But happy if you want to reach out, and yeah, probably happy to further discuss. But it's an international
I think
standard.
we can leave this discussion off for some other time. So one, you see, can you read the question in the last from Dr. Muhammad Irfan? Taking loss of pile load carrying capacity due to poor slurry. He's asking a quick comment on it.
Loss of pile capacity, time delays. Yeah, it's a big problem with time delays. We can lose a lot of shaft and base resistance, so it basically loosened. And I had a problem with exactly that, where we had to extend the piles more and more from 24 hours to 48 hours, and then we had to further reduce the reduction because the hole was open for longer. And actually, we did pile load tests. We did dynamic pile load tests. We drilled a number of piles, left them open. It was a job that was big enough, and it showed that basically after 48 hours, nothing happened. From 48 hours to a week, nothing happened. But again, this was project specific. But it's a significant time. I wouldn't be too concerned between 24 hours and 30 hours or something like that. But in the design, it's important to consider, can the crew drill the pile within 1 day? It takes it 2 days. And again, it's the very rarely 24 hours. It's mainly 12 hours or 36 hours because they start in the morning and finish in the afternoon. But they can have significant effects. But they usually taper off, in my experience, after 3 or 4 days and can't get worse.
Okay, he just mentioned any literature or references in this regard.
Unfortunately, I haven't found them. I had to go, my own references. How much reduction it is, not, but I think in our latest, at least, I think in the ICE specification, in the SPERBA specification for piles embedded retaining walls, they have something in the current New Zealand specification, which is a small country, but they have a pretty robust piling specification. I think it says 24 hours without reducing any parameters. But I would be more concerned about clay. I would be really more concerned about clay rather than sand, because the clay may provide this slippery surface layer, and this can provide big problems. I've seen shear strength values dropping to 10 or 20 kPa.
There are one comment from Dr. Irfan and one question from Abdul Rafi from Dar Engineering. So, Dr. Martin, if you can comment, say anything on the comment made by Dr. Irfan, and the last question, Abdul Rafi from Dar Engineering.
All right,
Quickly, please. And these will be the two last questions. Thank you.
Yep, all right. Sensitivity analysis to assess a performance plus minus 20 change in soil parameters. In common practice, it is often the biggest challenge for geotechnical engineers to select the most appropriate soil parameters. Is there a flow process you suggest in this regard which can help reasonable balance without overly leaning towards over-conservatism or over-optimistic design? There is no flow chart. I'm not aware of it, but what I would usually do is the best estimate. Be really honest with myself and say, look, probably takes a bit of experience, and then have this range and say plus minus 20 minus, and that gives me basically an assessment about my parameters. What is the difference in displacement? Is it 5 mil? It's probably not critical. If it's 20 or 30 mil, it's critical. And then again, if it's more shaft resistance related or base resistance related, for example, in New Zealand, we do a lot of base grouting. It's very expensive, but we pump some grout beneath the board pile base. That helps removing these things, but really thinking about that. And unfortunately, I'm not aware of any flow charts. Sorry. And then the last one is RQD, more relevant to assess the rock quality or the UCS and rocky strata, probably more the rock quality. Less than 15%, but becomes too difficult to drill since UCS is high. We had that in some instances, and again, it depends how fractured your rock is, and this is a very difficult thing. Look at the driller as well. Maybe sometimes the driller can't, or little issues, particularly in high strength rock. It's just the tension on the rock that fractures it. If it's too bad, for example, in fault lines from earthquakes, I would treat, even if it's high strength, would treat it as a very dense gravel in the design as a worst case scenario until we've done significant rock testing. But that requires really more sophisticated rock testing. But if it's less than 15%, I don't know if I would call it a rock, or if I would probably call it a very dense gravel. I know it reduces the resistance significantly, but that's what we've done a few times in these cases.
Larisch, can I show you photograph of my 3010, please?
Absolutely.
Otherwise, we are really short of time, so I have to conclude it also. Thank you
very
much,
much, sir. Thank you. Thank you.
So just my last comment, Dr. Martin, on the last question which you answered. So Abdul Rafi is in Dar Engineering. Most probably he's, I think, is quoting some issue from a case from Saudi Arabia. Just this is my comment that I have designed some transmission line tower foundations in Saudi Arabia in rock, and I have designed the rock anchors with an RQD of as low as 35. So as Dr. Martin has answered, it depends on the uniformity of the rock, what is the strength of the rock and how sound it is. So this was just a mere comment from me. Thank you. Thank you very much. So we have ended the Q&A session. Today we have we spent about 20 minutes more than our scheduled time. Thank you very much, all the audience, for bearing with us this extended time. And Dr. Martin, I don't know how to thank you. It was an honor for me to serve as the moderator for your lecture on pile design. I sincerely thank you for delivering such a rich and insightful session. Your ability to present complex engineering concepts with clarity and precision made the topic accessible and engaging for all. And I'm certain that our audience, especially the young and emerging professionals, gained profound understanding of the pile design through your expertise. Dr. Martin, thank you very much for your time, and especially I again apologize for giving you the trouble at such an odd time in New Zealand. So now some announcements I have to make. The next lecture will be on 13 September, and the topic is Building Resilience Through Forsenic Insights, a Structural Engineering Perspective. And our speaker is Engineer Rehan Wine. It's on 13 September. And audience who have registered for this program today, they can collect their certificates from 21st August onwards from our office, which is 14A1 Block P, Model Town Extension, Lahore. And before coming, if you want to confirm regarding your certificate, please call Ahmed Akram. His cell number is 0347462511. I repeat, the person to contact is Ahmed Akram. His cell number is 0347462511. Now, Dr. Martin, your shield and your certificate, inshallah, Sadia Naveed will dispatch through the courier service, should be with you in next 2 to 3 weeks. Now, today's program, I'm going to close this program. And before I end, I want to give special thanks to my team working behind the scenes for making this broadcast running so smoothly. Inshallah, we will see you again on 30th September. Audience and Dr. Martin, God bless you and thank you very much.
Thank you. It has been a privilege.